Swayam Prabha. Digital India. Educated India.
Hi, I am Radhakrishna Pillai. Today we will talk about mechanical properties, some properties which we could not cover in the previous lecture. So, these are some of the books which I use, and most of the material for today's lecture, it is mainly coming from the first book shown here by Mamlauk and Zaniewski. Now, we covered loading conditions, stress strain relationships, elastic behavior and elastoplastic behavior in the previous lecture. Today, we are going to focus on viscoelastic behavior and also looking at how temperature, load rate and the duration of the load affects the behavior of various materials. So, what is viscoelastic behavior? Okay. So, this is essentially a simultaneous viscous and elastic responses when materials behave in that way, and there is a delayed response to the stress or load applied. What it means is, let us say you look at the three graphs at the bottom. The first one is on elastic behavior, the second one is on viscoelastic behavior, and the third one is on pure viscous behavior. Okay. Now, in the first one, which is on elastic behavior, stress is proportional to strain, and you can look at that graph where you have the red curve, which is the stress curve, and this is as a function of time. Okay. Now, the blue or dark colored or the black curve is on the strain. It is essentially the blue color, but so you know which is the stress graph and which is the strain graph as a function of time. Now, you can see here the maximum stress is occurring or maximum strain is occurring at the same time when the maximum stress is occurring, or in other words, here also you can see it is happening at the same time. So, there is no lag between the stress and its effect on the material, which is strain. So, the time lag is insignificant or almost 0 in case of elastic behavior, or there is no phase difference. If you are looking at the viscous behavior, which is on the right side, this one, there is a phase difference of about 90 degrees, and what that means is there is again significant time lag, and also the stress is proportional to the strain rate and not just the strain. There is an additional word, strain rate, or rate is very important there. So, it is not in the first case elastic behavior, the stress is proportional to the strain. In the viscous behavior, stress is proportional to the strain rate. Okay. In most of our examples, we will talk about shear stress and shear strain. Anyway, we will come to that later. And this time lag, it actually depends on the material characteristics and temperature. Now, if you look at the viscoelastic behavior, there is also definitely a time lag, but that is in between the pure elastic case and the pure viscous case. So, you have a time lag or phase difference, that is this indicated by delta there. So, that is a typical behavior of a viscoelastic behavior. That means the strain is, if you look it carefully, the strain is followed by the stress applied. So, or there is a lag to the reaction, the the stress which is applied, or as stress if you look at as action and strain as reaction, then you can think of in that way. Now, here is an example to show this viscoelastic behavior. You can this lag you can see here. Let us say look at this sketch here, you have different time instants. So, at time t1, this compressed region of that spring. Okay. So, this is a slinky toy which you might have seen. So, when you play with this toy, it goes, as your hand moves down, it is not necessary that all the points along the spring is also moving downward. You might notice that when your hand is moving downward, some portion of the spring is actually moving upward, because it is still just about to react to the previous action of your hand, which was moving upward. So, you can imagine that scenario. So, here you can see from T1 to T6, this compressed region of the spring is actually moving, or it is moving downward, okay. Whereas the particles can move up and down, and then here also you can see some compression waves are there, okay, and here is the dilation waves. So, if I delete that, so these are the dilation waves, or they are, those regions are experiencing some expansion. Anyway, the point is that the action of your hand, if your hand is moving forward, it is not necessary that all the points in this spring is actually moving forward. It might, some point might be moving backward. So, there is this delay in the response to the action by hand, okay. Now, this delay is also, this is a very simple example to show you how or what this viscoelastic behavior and what that time lag, which I mentioned in the previous slide, means, okay. Now, when you go to real materials which we use, first thing to look at is what is this viscosity, and then how it affects the rheological behavior. So, now what is rheological behavior? It is the science, or rheology is the science of the deformation and flow of matter or materials. Now, what is viscosity? It is measure of the resistance to flow. Look at the examples here. First you have water, then blood, then you have oil, and then on the right end you have tar or asphalt or bitumen, all similar material. Now, viscosity is the measure of resistance to flow. That means, if you think about water and oil, which are probably more familiar to you, you can think water is less viscous than oil, especially if oil is not really, even if it is hot, water is less viscous than oil. So, you can look at the numbers here. This is the viscosity 1 centipoise, whereas for oil it is about 100 centipoise. Okay. Now, another thing is, this is again a time dependent phenomenon. Time dependent deformation is what we are looking at. It is now again the load applied and the reaction by the material, there is a time lag, there is a possibility of time lag. Now, here I am going to show you two examples which are probably the longest experiments, laboratory experiments which have been conducted, especially in this area. So, you can see the first experiment was started in 1927 in University of Queensland in Brisbane, and 80 plus years have passed, and then now you have, now 90 plus years, and now you have only 8 drops have been formed. In that experiment, what they did is they put the bitumen material or tar and then allowed it to form the drop and fall by itself, okay, without applying any. So, it is all under gravity load. Now, how long it takes for each drop to form? About 7 to 13 years. Okay. Now, what happened is in 2000 there was one drop and they missed that drop, the camera could not capture it. Another experiment of similar nature is happening in Trinity College, Dublin. That again started in 1944, and it is again an experiment on tar, or sorry, pitch in this case, and high viscosity and low flow is what they are studying. And actually the last fall was captured in camera, and you can see the video on this website which I have given at the bottom left corner. You can go to that link and watch this video on this experiment. And two more concepts here. There are two types of fluids when we talk about their shear rate and stress. One is a Newtonian fluid and the other one is non-Newtonian fluid. So, what is Newtonian fluid? Look at the graph here. You have shear rate on the abscissa and shear stress on the ordinate. Okay. Now, here the Newtonian fluid is the one which is following the green line, is this one. Okay. Now, the green line, so that is proportional, the shear stress is proportional to the shear rate or strain rate like we discussed earlier. So, there is this proportionality constant and that is a Newtonian fluid. One example is water. Okay. Now, these are linearly viscous material with the rate of deformation proportional to the stress which is applied. Incompressible material and they do not recover the shape once it is deformed. Okay, even after the load is removed, because we are talking about plastic deformation and not elastic deformation. Okay, this is plastic deformation. Now, non-Newtonian fluids are fluid which has the property which do not match with the Newtonian. So, that means anything other than the green curve over here, we can call them as non-Newtonian fluids. I'll go to the next slide. So, here you can see there is one curve which is given below the green curve and that is a dilatant, okay, or we can call it shear thickening material, okay, shear thickening material, and example is beach sand. Okay. Now, you look at the first photograph where you can see that person is standing on either a beach sand or muddy water. Okay. And what you will notice in such cases, you can think of when you went to the beach or something similar last time, when you stand there and as the water moves away from the bottom of your, from below your foot, what will happen is you will start feeling that the sand has become more and more stiff, or it becomes more and more stiff as water is moving away. So, that is how that is basically this kind of behavior over here, this kind of behavior. So, what I am saying is the slope of this graph, slope of this curve, if I take a slope here in the beginning when there are lot more water below your foot, this is the slope, but as you apply pressure, more water is removed from below the foot, and then you will see that the soil the sand becomes more and more stiff. So, if I take this as slope 1 and this as slope 2, slope 1 is smaller than slope 2, okay, or the slope keep increasing. That is what is dilatant behavior or shear thickening behavior. Now, let us look at shear thinning behavior or pseudoplastic behavior. These are all the materials above the green line. Okay. Now, one example of this is self-compacting concrete. As you can see on the photograph below, that is actually concrete being pumped or pumpable concrete, or the concrete which is self-compacting means usually when we compact concrete we use needle vibrators or some kind of tool to pack the concrete. Here in this case you do not need those kind of tools, and it is a very good technology. You will hear about this later in this course, but this material or this concrete you do not need any force to any external force or vibration to compact the concrete, it will flow by itself. How this is achieved is by changing the viscosity or the fluid properties, flow properties of the concrete. And what is the behavior here? I mean, typically for concrete we use something called Bingham model, which is shown here. You can see this, and this height here is what we call as yield stress, okay, for concrete, and where this point there is a deviation there, that is why we call yield stress. So, let us not worry about that for a moment. We will look at this curve which is pseudoplastic curve. Okay. Now, here just like I mentioned in the previous case of dilatant, the slope, look at how the slope is changing. Here the slope, imagine this is S1 and then here the slope is S2. Okay. Now, in this case S1 is greater than S2, or in other words, as the more and more shear rate is more and more load is applied, the stress slope is decreasing. So, this is what we call as pseudoplastic behavior, and in other case when the slope was increasing, we call it dilatant behavior. So, for application purposes, the self compacting concrete is very good, and because you do not need much energy, you need energy, like the amount of energy required to mix or place the concrete is less. Once it starts moving, it will flow by itself, maybe very slow, but it will flow and then fill all the small pores, small spaces, nooks and corners in the formwork, etc. It will fill up very nicely. So, it is a upcoming the use of this material is day by day increasing. So, you will hear this more later. So, two types of materials we looked at, and then some more examples of these pseudoplastic materials: thermoplastics, clay, tar, sludge, definitely concrete, paper pulp, grease, soap, all this. Okay. So, point is, once the material starts moving, then it becomes easier to move it further. Okay. Now, viscous behavior, which is permanent deformation due to short term loads. When we say a material is viscous, we are thinking about short term loads. Now, here short term load means the time of application of load is very, very small. Okay. Now, here in case of traffic, let us imagine you have a truck or a car moving along a road. Here you have every wheel of that vehicle is going to move on the road at very high speed. So, if you take a point on the road, let us say you take one point over here on this road, the time for which that wheel load is applied is very, very small, fraction of a second. It moves so fast, right. So, that is what is the short term load which is meaning. And then multiple traffic loads are also there. That means depending on number of vehicles which are there, you will have more and more traffic load will be more, the number wise. And what happens because of this? The material starts flowing, or the asphalt starts flowing laterally, okay, because of this load application. You can see here that there is a deformation also. So, there is a deformation like this, and then there are also movements which happens in this direction, Now, what do we call that? We call that rutting. Okay. So, this happens right along the wheel path of the road. So, you can see here, this is the path, the wheel path, and that is where you will see a depression like this one. Okay. So, we call it rutting, and this is happening because the material is moving or it is flowing. It is not flowing like water, but it is flowing in a very, very slow rate as every car passes through the road, or every vehicle passes through the road. Now, higher temperature can reduce the viscosity. That means, when during summer the flow rate or the speed of the flow will increase as compared to winter. And also you can see probably because this flow is more easy, or the material becomes less viscous, it might even bleed and flow upward on the road surface. So, this is an example where a person is pushing his finger through. You might have seen in some places during summer, the asphalt or the bitumen starts flowing upward, and then it gets all above the aggregates on the road surface. So, that is the example here. And very familiar to you, oil example here, when you heat it up, it is going to flow easily. When it is cold, it is going to, even you might have seen frozen in the oil in the bottle, in the winter season, it will get frozen. So, definitely viscosity is a function of the temperature. Now, another behavior which is important here is creep. Here also we are talking about permanent deformation, okay, But this is mainly due to the long-term sustained load, not short-term load like in the case which we just discussed in the previous slide, which is viscous behavior. Here permanent deformation and long-term sustained load. Now, where does this typically happen? In materials where you will see ionic, covalent and such bonds, and also amorphous materials. Now, examples are here: concrete, you have wood and metals. Okay. Now, in the concrete, how this happens is because of this long term sustained load, there could be micro cracks which form inside the concrete. Now, it is not like large crack which you see outside, but we are talking about micro crack which forms inside the concrete. Here is an example of a bridge which showed creep deformation, which took several years to show, not in 1 day or 2 days, not immediately after the construction. After long time, because of the load, the heavy weight of the concrete itself, it started deflecting downward. You can see creep deflection, it is written here. So, this is the one very good example demonstrating that concrete can actually creep. Okay. And here we talk about flexural creep. Now, another example is wooden sleepers below the railway tracks. You can see here the wood, imagine you have a particular thickness, and if that wooden piece is used without any pre-compression or pre-loading, then maybe after the rail tracks are placed, after the train starts moving, you will see more deformation, or the wood gets compressed by, let us say, a thickness of delta x. Okay. Now, in a case 2, if I preload the wood, then what will happen is that delta x can be reduced. So, when I say delta x, it is the deformation after the rail track is placed and during the service, right. Now, so people actually what they do is they pre-compress the the timber before they place it below the rail track. So, because of that, the compression which is happening after the rail track is placed is going to be minimal. So, preloading or pre-stressing of wood is very useful to reduce the creep deformation after the installation. So, maximum possible compression you do it before the installation, so that after installation it is less. Another case is metals, where creep happens when the temperature of the ambient temperature or the temperature of the metal itself is more than about 30% of its melting point. If it is less than that, then the creep deformation is not very significant. Okay. Now, another example is about pipelines. You can see here, I will show, look at the picture here, but the same picture I am going to show in the next slide. So, it will be more clear there. So, you can see here inside the red region, you can see the pipe is deformed. Originally, it was a straight line between the clamps. This is the clamp 1 and this is the clamp 2. Okay. So, originally it was placed as a straight line, and then as time passes, the weight of the pipe or the fluid which goes through that, it was continuously acting downward, and because of that it started sagging, or the sagging we are going to call it as creep behavior, because it is a permanent deformation. It is not just elastic deformation, it is permanent deformation, and also this sagging is happening over a period of time, several decades. Look at here, the first case here, it is 75 years, second case here we are talking about 70 years. So, this becomes very important factor. The creep behavior is very important when you talk about any structural element or any material for that matter, if your structure is designed for several decades. If whatever you are building is meant to last only for few years or just couple of decades, maybe creep is not, but it depends on the structure. I am not going to say it is not important, it depends on the structure and the size and shape of the structure. So, various factors, okay, because the cumulative deformation is what is that we look at. So it's very, very important to consider, but unfortunately some places we don't consider, and then we see a lot of problems like this, and it also affects the aesthetics. One example where you can see this creep behavior very easily is when you go on the road, look at the deviators or the barricades, the barrier, not the barricade, the barrier between the lanes on our highways and roads. You know, I am talking about those black and white painted barriers. You will see electrical conduits placed on that, you know, fixed onto the side of that. Have you seen anywhere where it is straight line? It's very difficult, right? Because all of them you will see that from clamp to clamp it will have a sag. Okay, so clamp to clamp, I am going to draw it here. So I am talking about these kind of systems on the road, you know. So you will see a electrical conduit going like this it will go. Okay, so this is what we are talking about. This sag is because of the creep. And what is the material used for the pipe? The electrical conduits are either made of some sort of plastic, they are not metals all the time, some sort of plastic, and now they are all exposed to sunlight. And considering our climatic conditions, the temperature is very high, and probably that is making the conduit material very soft. And when it is soft, it starts you know, sagging a lot, and then it undergoes creep deformations. So next time when you are on the road, you can look for this, it will be interesting.